This video is the first in a short series on the aerodynamics of wind turbines. While I will not talk about wind turbines here, the topics have been chosen to match those needed to derive the best theory. If you have taken a basic course in fluid mechanics, you have probably heard about this content before. But it can still be a useful repetition, as I may teach them in a different way. I also want to remark that this video will not replace a basic course in fluid mechanics, as the explanations will be very brief here. The content of this video is as follows. We start by an introduction to pressure and shear stress. Then we will focus on the basic equations on integral form. Focus will be on the continuity equation and the momentum equation. We will then finish by going through the energy equation and Bernoulli's equation. With this, let's get started. Our first concept is pressure. We start by introducing the concept of a cross-section. This is a virtual surface that we can introduce anywhere in the fluid, and it does not have to correspond to any physical object. We can use this concept to study the forces inside the fluid. Assume that we have a force that is evenly distributed over this cross-sectional area. As the cross-section is infinitely thin, we can assume that we have equal forces from both sides to make the sum of the forces zero. This follows directly from Newton's second law as long as you have a continuous flow. Let's represent this force distribution by a single force Fn, where n stands for the normal direction relative to the surface. We can now define the pressure as the force per unit area, which can be calculated by dividing the force with the area. It's very common in fluid mechanics to use variables such as pressure, density, etc., as the size of the fluid often can be hard to define, while the pressure will be more similar between different cases. We will start by studying how this pressure varies with depth. Assume that you have a container full of water. Define a horizontal cross-section somewhere in the water. Now let's study the fluid above this cross-section in the orange rectangle. Due to its mass, there will be a force of gravity acting on the mass. This is calculated as mass times acceleration of gravity. The mass is the density times the volume. Here, the volume is denoted as V with a strike through. This is to avoid confusion with the velocity. Call the base area A and height of our chosen volume h. The volume can now be expressed as h times A. We can now identify the force on our cross-section as the force of gravity. We can also update the equation. The force of gravity is counteracted by our pressure force from below. Insert the force of gravity into the equation. We can cancel the area. And reorder. This is our equation for how the pressure varies with depth. We can see that we have a linear increase, this assuming that we have no flow velocity. The pressure we have in the expression is the relative pressure, also called gauge pressure. We also have the absolute pressure, where we include the atmospheric pressure. The reason we normally neglect the atmospheric pressure is that it usually acts equally on all sides of an object and thereby do not contribute to the force. We can also add the forces in the tangential direction of the cross-section, call it Ft. When we calculate the force per unit area, is now called shear stress, denoted by tau. These forces are caused by friction in the flow when we have a variation in the velocity. Here we have a flow in the x direction that varies in the y direction. The shear stress will now be given by the dynamic viscosity mu and the velocity gradient. For fluids such as water and air, which are called Newtonian fluids, the viscosity can be considered as a constant in this equation. As the term dynamic viscosity divided by density appears frequently, it has been given its own name, which is kinematic viscosity. Finally, we should note that we can have shear stress in the other direction. The shear stress is actually tensor, the total of 9 components. The component we have here is the y-x component. Y as the surface as normal in the y direction, and x because the force is in the x direction. So how do we calculate the force if we know the force per unit area? Here we could just multiply by the area, but the general case is more complicated. Let's start by looking at pressure force calculations. We have a container with water and we want to calculate the force on the half circle. The pressure is always acting opposite to the normal direction of the surface. Could we simply calculate the force as pressure times area? The equation is written in red because the answer is no. If we compare the length of these two, they are different, as pressure increases with depth. Let's change the equation to apply for a small area element instead. For this small area element, we can assume constant pressure. We are still missing something though, and that is the direction of the force. Let's add in the normal vector pointing outward from the surface. We can see that the direction of the force is minus n hat. This expression can be integrated over the area. The left-hand side is just the force. We can place the minus outside the integral. This is our general equation for calculating pressure forces. Let's look at the figure again. We will now add shear force in the tangential direction. The general expression for shear force is to use the following expression. The double lines above the shear stress indicates that it's the full tensor we use. For our purposes, just knowing the definition is sufficient, hence we will move on. Our next topic is to review flow integrals before we continue any further. Let's assume that we have a pipe with inlet velocity v and area in. Define the cross-section with area A, where A at the moment is the same as A in. First, we'll introduce the volume flow, which is defined as the time derivative of the volume. Units is cubic meters per second. Let the blue box represent the flow particles that will pass through the cross-section during the time delta t. Call this volume delta v. Let's move the system forward in time. The block has area A and the length is v times delta t. We can now calculate the volume as the area multiplied by the length. Divide both sides with delta t. Let delta t go to 0, which converts the deltas to derivatives. dt over dt is 1 and can be cancelled. And we have that the volume flow is the area multiplied by the velocity. But what happens if we change the angle on the cross-section? Call this angle theta. We can calculate the new area as A in over cosinus theta. Logically, the flow through this cross-section should still be the same as it covers the full pipe. But as the area is larger, so we need to compensate for this in some way. Let's introduce the normal vector and add in the velocity. Now, let us replace the velocity with the dot product between it and the normal vector. The angle between the velocity and the normal vector is theta, which is more easily seen if we increase the value of theta. The dot product can be calculated by using cosinus between the vectors. Insert a new area. Cosinus cancels and we get back our original expression. Hence, By adding in the dot product, we can now handle any direction for the cross-section. Our next case to consider is if we have a moving cross-section, called the velocity VCS. Let's run the same animation again, but with a moving cross-section. The area is still A and the full length is still V times delta T. The length that the cross-section has moved is VCS times delta T. This means that the length of the part that actually passed through the cross-section is V minus VCS times delta T. For moving cross-sections, we should therefore replace the velocity with this expression. Another way of looking at it is that we should use the relative velocity, which is the velocity in the reference frame of the moving cross-section. Finally, the last case we need to consider is that the velocity varies over the cross-section. Instead of multiplying with the area, we should therefore integrate over the area. Another case that would require integration is curved cross-sections as the normal vector varies. This is already covered by our current expression though. Hence, we have a general expression for the volume flow. Let's move to the mass flow. This is defined as the time derivative of the mass. Here we call it m dot. Let's do the same as before and consider the block of particles. The area is still A and the length is V times delta T. Mass is density times volume, or density times area, velocity and delta T. Do the same as before and divide both sides with delta T. And let it go to 0 to turn the expression into derivatives. dt over dt cancels again. And we can see that we got the previous expression multiplied by the density. First, save our volume flow expression. We can now convert the expression to the mass flow by multiplying with the density. Save this one as well. I also want to update the original expression for the mass using the density. In case the density varies, the mass should be calculated by integrating the density over the volume. I want us to stop and think about what happened when we moved from volume flow to mass flow, as the mass is volume times density. What we get is that in both the integral for mass and the integral for the mass flow, we just multiplied by the density. All the other properties we can calculate in a similar way. So by just multiplying the integrals with some normalized property. In fact, this will work basically the same for all extensive properties. If you are unfamiliar with the terminology, an extensive property is a property that varies linearly with the mass. Now, replace M with any extensive property B and let small b be that property per unit mass. And do the same for the flow integral. As an example, let B be the internal energy U. Small b is now the internal energy per unit mass, which is called the specific internal energy denoted by small u. If we double the amount of mass, we should have approximately twice as much internal energy. This means that this property is okay. But it would not work for the temperature though, as the temperature stays the same if you double the amount of mass. Let's restore the equation to using B, which can be any extensive property. To summarize, we have an equation to calculate the amount of any extensive property inside the volume, and we have an equation to calculate the flow of the same property through a cross-section. We will now go through Reynolds transport theorem. This is the core for writing the fundamental equations on integral form. To give a brief description, we want to study a given volume in space with fluid. However, the equations we are used in classical mechanics are for a given object. This means that we need a way of converting our classical equations from a fixed mass into an equation for a volume that can have a flow of particles through its sides. This is what Reynolds transport theorem will do for us. We are going to derive it for any extensive property, and will therefore get several equations in one derivation. Start by creating a container with one inlet and one outlet. We will now define a control volume CV, which in our case is inside of the container. The idea is that we want to do calculations for this chosen control volume. We call the surface of the control volume the control surface, denoted as CS. Call the inlet velocity V in and the area of the inlet A in. We will also have a density in and some value for our normalized property B in. Call the outlet velocity V out, area A out, and we'll also have a B out and density out. Assume that this represents time t. Call the amount of our extensive property inside the control volume B CV of t. We'll also call the amount of property B that will enter the control volume during one time step delta t B in. As our next concept, we will introduce the system, which always contains the same particles independent of time. This is to match our classical mechanics equations, which generally assume this. The system at time t will contain the particles in the control volume plus those in delta B in. Make a copy of the system and let this copy propagate one time step. The particles in delta B in have now merged with the control volume, and some other have left the control volume. Call the particle of those delta B out that left. The darker particles should now be exactly the same particles for both cases. We can thereby calculate our property B for a system at this new time t plus delta t as the value inside the control volume BCV t of delta t and the amount that left the control volume delta B out. We are now going to calculate the difference by subtracting the first from the second. We can remove the parentheses. Write the BC terms next to each other. Divide everything with the delta t. The first term can be identified as the definition of the derivative. The second term is also the definition of the derivative when delta t goes to 0. As we let delta t go to 0 for the other two, do the same here. We can now recognize our flow integral, which we can insert for the outlet. For the inlet, we need to be a bit more careful though, as the normal vector is opposite to our flow velocity. The dot product will therefore generate a minus sign here. We can now see that both flow integrals have the same form with the same sign. If we had additional inlets or outlets, they would also look the same. We should also note that the integral would be 0 if we study the container wall, as no flow can go through a wall. We can therefore combine these into the integral over the entire control surface. Finally, replace BCV with the integral over the control volume. This is Reynolds transport theorem, which works for any extensive property. Small b can be calculated by dividing the property with the mass. To demonstrate this equation, let us use it for the mass, which is the easiest example. Set b sys equal to mass, we can directly see that small b becomes 1. Let's insert these into the equation. If you remember the definition of the system, it should always contain exactly the same particles or exactly the same mass. Directly from this definition, we see that the m sys to t is strictly equal to 0. Let's explain the individual terms of this equation. This term is the mass inside the control volume. The time derivative of it then becomes the change of mass in the control volume. The surface integral is the mass flow through the walls of the control volume. Therefore, the continuity equation states that the change of mass inside the control volume is equal to the flow of mass through its walls. The equation describes conservation of mass. We cannot create or destroy mass here. Let's illustrate the equation with an example. We have a container of water with one outlet. The container has base area A and height capital H. The outlet diameter is small d. Now assume that we have a cylinder that can enter the container from above. The cylinder has diameter d and moves with speed v cylinder. When it moves down, it will push flow out through the outlet. Assume that it currently has traveled the distance h into the container. Then, what is the flow speed at the outlet? Start by defining the control volume as the water inside the container. We can assume that the control volume is stationary. Moving control volumes are normally only used when dealing with the moving objects. We can see that we have one outlet. Everywhere else, the surface integral is 0. Add in the normal vector, which always points outward from the control volume. We see that the normal vector has the same direction as the velocity. And the dot product becomes positive v out. The surface integral can now be written as the density times the average velocity, multiplied by the area. As long as you use the average velocity, it doesn't matter if the velocity varies over the cross-section. The area can be written as pi d squared over 4. We can assume that water is incompressible and place the density outside the integral. This integral will now be the volume. The volume can be calculated as the large cylinder volume h times h minus the cylinder. Here I call the base area of the cylinder acyl, which is pi capital D squared over 4. The only variable that varies with time is small h. The h dt is the cylinder velocity. Move to the right hand side. Density and pi over 4 cancel. We can solve for the average velocity. And we see that the answer is the cylinder velocity multiplied by the ratio between the diameter squared, which ends our example. Let's do one more example with a pipe that changes its diameter. Call the pipe inlet velocity V in and outlet velocity V out. We can now define the control volume with the inlet as the wide diameter and the outlet at the narrow part of the pipe. We add the normal vectors out from the control volume. We can also call the inlet area A in, inlet density ρ in, outlet area A out, and outlet density ρ out. Same as last case, we use a stationary control volume. We'll also assume stationary flow, which makes the time derivative 0. Split the surface integral into one integral for the inlet and one for the outlet. At the inlet, the velocity and the normal vector have opposite sign, which gives that the dot product becomes minus V in. Place the minus outside the integral. We can remove the integral by writing this in terms of the average velocity. For the outlet, the velocity and normal vector have the same sign, giving positive v out. We can write this in terms of the average velocity as well. Finally, move this to the left-hand side. This is the continuity equation for stationary pipe flow. It states that the mass flow is constant for all cross-sections of the pipe. Let's move to the next equation, the momentum equation. Here we will use the momentum as our extensive property. As the momentum is mass times velocity, small b becomes the velocity. Insert into Reynolds transport theorem. The change of momentum for a system of fixed mass is according to Newton's second law, the force. Here we write it as the sum of all forces. We can hereby see how Reynolds transport theorem allows us to directly convert Newton's second law into operating on the fluid in a control volume instead. This equation will be a bit more complicated to work with than the continuity equation, as it's a vector equation with 3 directions and because we have to consider the forces. The individual parts can be explained similar to the continuity equation. The volume integral is the momentum inside the control volume. When we add the time derivative, we get a change of momentum in the control volume. The surface integral is the flow of momentum through the walls of the control volume. Finally, we need to consider the external force on the control volume. So, what can be an external force acting on a control volume? One force we used earlier is the force from the pressure. We showed in the beginning of the video that the pressure force is calculated by integrating the pressure over the surface. Here we should use the entire surface of the control volume. A second force we talked about is from the shear stress. This can also be calculated by integrating over the entire surface. A third common force is gravity, which is mass times acceleration of gravity. Here I have written mass as density integrated over the control volume. Now we're going to look at what happens if you have an object inside the fluid. Assume that you have a container with water and an object inside it. The flow is acting with a force on the object. Call this force F object. This force can have any direction. I have drawn it upwards here due to buoyancy. The normal vector of the object is pointing outward from the object. We can now calculate the force from the fluid as the contribution from pressure and shear stress. How does this relate to a control volume? Due to the mathematics we used to derive the equation, we have to assume that the control volume is one simply connected domain. Here, we only want to have the fluid inside the control volume, so the object is outside. We can therefore choose the following control volume with the object outside. Let's divide the control surface into 4 different areas. Call the outer area A outer, call the area from the top down to the object A right, the area next to the object A inner, and the area from the object up to the top A left. Let us also add in the normal vector that is pointing outward from the control volume. We can start by calculating the pressure force for this control surface. Split the surface into the 4 chosen areas. Now, let's decrease the distance between the left and right areas. If the distance is small enough, we can approximate that A left is the same as A right. Their normal vectors have opposite directions though. This means that as long as the pressure is continuous, the two integrals will cancel. We can do the same for the shear force, and the terms will cancel here as well. Let's compare the inner integral with the force on the object. We can see that A inner is the same area as A object, but the normal vectors are opposite. Hence, the integral over the inner area is minus the pressure force on the object. With the same argument, we can see that the shear force on the inner area becomes minus the shear force on the object. If we combine these results, we can see that the force on the object can be inserted as an external force, but with a minus sign. Another way of looking at it is to consider that F object is the fluid's force on the object, but the momentum equation, the force we use, is the object's force on the fluid, which is opposite to the fluid's force on the object, hence the minus sign. When we set the force on the object as an external force, we should remove it from the pressure force and the shear force. Finally, we can rename A outer to CS to make the expression look as before. We can consider the force on an object as an external force in the case that the object is inside the control volume but not a part of the control volume. I usually recommend that we try to be structured when using the momentum equation. I will therefore give you a suggestion of which steps to take when using the equation. Start by drawing a figure of the problem that you want to solve. Second, define the coordinate system that you are going to use. The first choice is about coordinate system is which type, such as Cartesian or cylindrical. We also need to define the directions of our base vectors. We can choose either a moving or a fixed reference frame. Moving reference frames are mainly interesting for moving objects. The next step is to define the control volume. This is the most important step, as it's the position and size of the control volume that determines the results. If we choose a bad reference frame, it will make your calculations harder, but you will still get correct results. If we choose the wrong control volume, the results will be wrong. The general guideline is that the phenomena that you want to study has to be inside the control volume, and no other phenomena that can affect the results are allowed to be inside. For the control volume, we should choose if it's moving or stationary. Remember that the speed of the control volume has to be given in your chosen reference frame. You have to choose what's included in the control volume. The equation itself doesn't care if the mass or if it's a solid, so you can let solids be a part of the control volume, or you can let them be external forces, as our recent case with the submerged body. As a next step, we can list all external forces that contribute. Further, we need to consider if we need additional equations to solve our system. It's very common that we need to combine the momentum equation with the continuity equation to fully define our system. Finally, it's time to solve the equation. Let us demonstrate this with an example of a pipe bend. We want to calculate the force on this bend due to the fluid inside the pipe. Step 1. Draw a figure of the pipe. Call the inlet velocity V in and the outlet velocity V out. Call the inlet area A in and the outlet area A out. Call the inlet pressure P in and outlet pressure P out. Now, we have a figure to work from. Next step is to define our coordinate system. We can choose the system we already have down in the corner. It's a Cartesian system. We have the directions and we let it be a fixed system, as the pipe itself is fixed. Now this step is completed. It is time to define a control volume. As we study the bend, it has to be inside the control volume. Choose the volume to be outside the pipe and contain the bend. We place it outside as the pipe should be in the control volume if we want to calculate the force on the pipe. We add in the normal vector of the control volume. We choose a stationary control volume and we only include the fluid in the control volume to make the pipe an external force. We are now done with this step. Next, we list all forces. We start with the pressure force, and we assume that all pressures are gauge pressures. This means that we can neglect the pressure everywhere outside the pipe. For the inlet, we have the pressure P in acting on the area A in the positive x direction. For the outlet, we have P out acting on area A out in the negative y direction. We can write the minus in front of the expression. Our next force is the shear force. Note that as our control volume is outside the pipe, it does not have contact with the flow and can therefore not give a shear force there. The only place it could act on is the inlet and the outlet, but we do not have any relevant shear forces in these directions, hence we can set it to 0. To get the shear force, we would have needed to place the control volume inside the pipe instead. The next force is gravity. In this example we will neglect it though, but it does exist. Finally, we have one object, which is the pipe. This is the force we want to calculate. We insert it with a minus sign as we want to calculate the force that the flow is acting with on the pipe. The final step before we start to solve the equation is to consider if we need more equations. Here the answer is no, as we have been given so much data. A typical use of the continuity equation would have been to calculate the outlet velocity if we only knew the inlet velocity. Finally, let's start the calculations. We start by making some additional assumptions to make this easier to solve. First, assume stationary flow. Second, assume constant flow over each cross-section. This means that the velocity is V in over the entire inlet area and the velocity is V out over the entire outlet. We will also assume incompressible flow, which means that we can consider the density as a constant. Start by replacing the sum of the external force with our calculated forces. Stationary flow means that this term is 0 as it's a time derivative. A stationary control volume means that this term is 0. Let's split this integral into one integral for the inlet and one for the outlet. From our coordinate system, we see that V in is in the positive x direction and V out is in the positive y direction. At the inlet, the velocity and normal vector have opposite directions. This turns the dot product into negative V in. We place the minus outside the integral. The vector V is V in x hat. We can combine the V in terms. As we assume constant flow over each cross-section, this integral is just a multiplication with the inlet area. At the outlet, the velocity and normal vector have the same direction. This turns the dot product into positive V out. V is in this case V out y hat. We combine the V out terms. And the integral becomes a multiplication with A out. We want to solve for F pipe. Move it to the right hand side and reorder the terms. Combine the X hat terms. Same for the Y hat terms. And we have our final expression for the force acting on the pipe. The direction will be down to the right in the figure. This concludes our example, and we will now move to the next equation. The next equation is the angular momentum equation, which we will only mention briefly. Let BCs be the angular momentum instead. Small b now becomes r cross v. Update Reynolds transport theorem with these properties. From classical mechanics, we have Euler's second law, which states that the sum of all moments of force is the change in angular momentum. Here we use m for moment, but in the upcoming wind power lectures, Q will be used as the torque to match what is used in literature. Replace this with the sum of the external moments of force, and we have the angular momentum equation. This equation should be used in a very similar way as we used the momentum equation. So you can follow the steps given but change the force to the moment. This is all I want to say about this equation here, and we will move on to the next equation. Our next and final application of Reynolds transport theorem will be the energy equation. This one is a bit more complicated to derive, so we'll split it up into smaller parts. Assume that energy is given by the potential energy EP, the kinetic energy EK, and the internal energy U. Let us start by looking at the potential energy given by mgz. As we use z for the vertical direction, let's first update our coordinate system to have z upwards in the figure. We can also drop the x hat for the inlet velocity, as energy is a scalar property. We also need to add in the height of the inlet, z in. Assume that the pipe is so small that z in is a good approximation for the entire inlet. We can also drop the direction for the outlet and insert the elevation of the outlet z out. Note that all properties should be given at the inlet and outlet of the control volume. Hence, assume that properties given for the pipe inlet is the same as for the control volume inlet, and the same for outlet. First, insert expression for the potential energy into ECs. Now, we will investigate what happens when we take the time derivative of the potential energy, which is the power. Let us look at the case of a vertical pipe. We add in a control volume with height z and base area A. We can now add some mass particles that travel down through the pipe. We see that the height of the control volume is constant, but the mass particles move. Hence, when we work with the control volumes, the time derivative will act on the mass, which will turn it into the mass flow. We call the mdt m dot. The mass flow can also be given in terms of the average velocity, the density, and the area. Next, Let us consider the kinetic energy given by mv squared over 2. First, insert it into the equation for ease. Now, let's calculate the time derivative again. Just as the previous case, the time derivative acts on the mass, turning it into the mass flow. The mass flow is velocity times density and area. There's a problem with this equation though. What if the velocity varies over the area? We cannot use the average velocity here as the kinetic energy is not linear with the velocity. Let's turn the expression into an integral over the area instead. We can combine the velocities. Multiply and divide by the cube of the average velocity times the area. Place these outside the division. We can now introduce the velocity correction coefficient alpha, which is this term. Split this cube. This can be identified as the mass flow. We can see that for flow of kinetic energy, we need to introduce the correction coefficient alpha to account for that the flow velocity can vary over the cross-section. When we use this in practice, we can often calculate the value for alpha in advance. For example, laminar flow in a circular pipe has alpha equals 2, while turbulent flow has a value close to 1.05. If the velocity is constant over the cross-section, alpha is 1. Our third concept to talk about is work, which is given by the force multiplied by the distance. As the force should be applied in the direction of the distance traveled, we use the dot product. Again, we want to calculate the power by taking the time derivative of the expression. The time derivative acts on the distance, which becomes the velocity. One type of work we often deal with here is called flow work. This is work performed by the pressure force. We can insert expression for the pressure force on the control volume. Change the order of these to make it similar to our other expressions. Also multiply and divide by the density. We can now set up an expression for the change of energy of the system. First, the energy can change through heat flow, which we call dq dt. Second, we can add energy to the system through work performed by a pump. We can also remove energy from the system with work performed by a turbine. Note that we use a plus sign if we add energy and minus if we remove energy from the system. Finally, we can add or remove energy through our flow work. As it is defined above, it adds energy and we include it with a plus sign. You may see it defined with the opposite sign in other literature though, depending on if you consider work performed by the system or work performed on the system. We start by renaming the heat flow to Q dot. For the pump, we will rewrite the expression on a similar form as the flow of potential energy. We assume that power is the mass flow times G and the pump head HP. HP can be seen as the altitude that the pump can add to the fluid. We will do the same for the turbine and introduce the turbine head HT. Finally, we insert our expression for the flow work. As a last step before we are ready to use the Reynolds transport theorem, divide by the mass. The mass cancels. The internal energy per unit mass is the specific internal energy. D is the T is B for Reynolds transport theorem. To set up the energy expression on the general form would be quite complicated. Hence, we are going to introduce some assumptions to simplify the expression. Our first assumption is that the flow is stationary. We also assume a fixed control volume. We can now set the entire volume integral to 0. And we can set VCS to 0. Let us insert expression for dE sys dt. And insert expression for B. These two expressions are in the same form, and we can merge them into a single integral. We will now add the assumption of incompressible flow. We will also assume that we only have one inlet and one outlet, as shown in the figure. This assumption can be used to divide the surface integral into one integral for the inlet and one for the outlet. Let the flow velocity have its own integral. We can assume that this term is constant and place it outside the integral. I have added the index in on all variables here to show that we use the values for the inlet. Our next assumption is that the normal vector is parallel to the velocity. This is a minor assumption, as we can always choose our cross-section to fulfill this condition. At the inlet, the normal vector and the velocity have opposite directions, which will turn the given integral into minus the mass flow. The velocity integral is the flow of kinetic energy through a cross-section. We can insert the expression we calculated earlier. Remember that the minus sign from the dot product applies here as well. We can do exactly the same for outlet. Here we get a plus sign from the dot product. Move the inlet terms to the left-hand side. Move turbine to right-hand side. Divide all terms with the mass flow. Move these to the right-hand side. Divide all terms with the acceleration of gravity. I want us to look closely to these terms. We have the difference in internal energy and heat flow. This means that they represent the energy converted into internal energy and energy lost due to heat flow. Combined, these represent the energy lost in the system. We will therefore give them their own name, which is the head loss, HL. Finally, reorder the left-hand side. This is the energy equation. There are some more assumptions one usually added to the list. The first is no other thermal terms. This means that we can have pumps, turbines and head loss, but no more external terms that can change the energy of the system. We also assume constant temperature, which means that our loss is so small that we do not affect the temperature in any significant way. To quickly summarize the names of the new terms, HP is the pump head, HT is the turbine head, and HL is the head loss. From the energy equation, we can derive the Bernoulli equation. This is basically a simplified version of the energy equation. First, neglect the pump, the turbine, and all losses. Now, introduce a streamline into the pipe. For simplicity, we assume that the center line is a streamline. A streamline indicates the direction of the flow. Hence, a fluid particle should travel along this streamline. We can now decrease the size of the control volume to center it around this streamline. As long as the control volume encloses the streamline, we can still assume that we have one inlet and one outlet and no flow through the sides of the control volume. If the control volume is small enough, we can assume constant velocity over a cross-section, which means that alpha is 1 and we no longer need to average for the velocity. Multiply all terms with density and g. This is the Bernoulli equation. As the equation is symmetric, it's common to use indices a and b instead of in and out. The equation states that this term is constant between inlet and outlet. Hence, it's common to write it with a constant instead. Let's summarize the assumptions for Bernoulli. The first assumption is stationary flow. The second is incompressible flow. A third assumption is no losses, nor any pumps or turbines. Finally, the 2 points we compare should be on the same streamline. There's an alternative condition which states that the points do not have to be on the same streamline if the flow is irrotational. This alternative condition cannot be seen from our derivation here. Instead, you should derive Bernoulli by integrating Navier-Stokes equations if you want to prove this. Let us end this video by doing an example of how you can use Bernoulli's equation. Let's assume that you have a Venturi pipe, which is a pipe with a narrow section. We have installed the 2 vertical pipes that are used to measure the pressure at the given positions. The velocity at both the inlet and the outlet is V pipe. The inlet diameter is capital D and the narrow section has diameter small d. The height of the water column in the right pipe is capital H. Assume that all these values are known. Now we want to calculate the height in the left pipe, called small h. The first thing to do when solving problems with Bernoulli is to choose points A and B. Place point A at the narrow section, place point B under the right pipe. If we assume that the center line is a streamline and no losses, this should be okay. Both points are on the same altitude, hence these cancel. The pressure at point A can be calculated using hydrostatic pressure, which we used right in the beginning of this video. Insert into Bernoulli. We can use hydrostatic pressure for point B as well. Insert this pressure into Bernoulli. The density cancels. We need one additional equation to determine the relationship between VA and VB. For this, we can use the continuity equation for pipe flow. In this problem, we will assume constant flow over each cross-section. Hence, we can drop the average. Bernoulli requires incompressible flow, so we assume equal density. This area is pi d squared over 4. And this area is pi capital D squared over 4. Pi over 4 cancels. Solve for VA. Insert into Bernoulli. Take the square of each term individually. Move to the right hand side. VB squared over 2 is a common factor. Divide by G. Finally, we can identify VB as V pipe. This is our final expression for the height h. This example will also mark the end of this video. Thank you for watching.